Okay, so we wrapped up chapter 2 last time. If you've been through the textbook, I've skipped one section in chapter 2 called network equations. I skipped that on purpose. We will sort of include it in something later on chapter 6. I will sort of bring it into the picture without spending time on it and solving specific problems on it, okay? So that's why it's important to go through the textbook as well as pay attention to what we're doing here, because you may get confused if you don't, right? So anyway, so we'll start chapter 3. Today the topic of chapter 3 is power transformers. So power transformers are really the workhorse of the power system. So this is really why we have an AC power system today. It's because of these transformers that we have available for our use, right? So you see them probably a lot. You see smaller ones, maybe inside smaller in these distribution stations, small substations that you'll find closer to your neighborhoods, and you will see very large ones when you're driving along the highways. Or if you've interned in an industry or a factory, these things should be pretty familiar. So if you want to sort of dissect the picture a little bit and see, so that you have an idea when you're driving around what the different components of this thing are. So obviously this is the transformer here, and then these long sort of funny looking devices or inputs, and if you see they have a corresponding similar ones at the output. They're not clear from the picture here, but they have 3 inputs coming in, right? And you will have 3 of those coming out, and you will have these are a little bit longer than these. Okay, so these are nothing but insulators. So this is the high voltage uh, coming in or coming out, and this is the high voltage coming in or coming out. Of course, the shorter ones, if this is shorter than this, it means that the higher voltage is on this side, right? So you need a higher voltage. So basically, you have a live conductor coming in. So this is a live conductor with voltage on it, and the chassis of the transformer, the metal itself, is grounded, and we will talk about why it's grounded when we talk more about protection, okay? But typically, the chassis itself, the body itself is connected to ground, mainly because, let's say a human passes by and touches the body. The human passes by and touches the body, and it's not grounded, and let's say an insulating wire, a wire inside broke its insulation and is touching the chassis. For some reason, the winding is touching the chassis from inside, or there's a conductive path inside connecting the high voltage to the chassis, then the chassis itself will be a big electrocuting device, right? You touch it, you die, right? So that's why typically the chassis will, for safety purposes, will be connected to ground, right? So if you have a live conductor coming into something connected to ground, you have to make sure you insulate properly, right? Otherwise, you will have arcing and flashovers occurring, right? So these are insulators at the input and insulators at the output of the transformer. The transformer itself, the windings and stuff you cannot see from this picture here. It's inside this device. There are transformers that this is an oil field transformer. There are oil field transformers and there are dry type transformers. These are the major 2 classifications, either oil field or dry type. Dry type will be for lower power, lower power, lower power, or places where you have indoors. When you need them to, when we need to put this indoors, you don't want to make. You want to make sure that you don't put oil inside a place that, for God's sake, if the oil spills or there's a leak or whatever, you don't want it to be there, right? The reason we would have oil field transformers, or they're the most common, or they're higher power transformers, typically oil filled, is because the oil is typically used for cooling, right? So if you see here, there will be a big oil tank. This will be a big oil tank up here, and typically, if any fluid or any air or fluid, right? If you heat it, what happens to it? Expands. Okay. And then how about if you have this fluid in a closed area and you have cold and hot fluid? What happens to the cold fluid? Cold fluid will be at the bottom and the hot fluid will rise, right? So that's how we cool a transformer. So we have the oil inside the transformer. When it gets hot, it rises, right? Naturally, it can do that naturally, or it can do that by force, by a pump, right? So if you and we will see the ratings of the transformer. So actually these transformers have multiple ratings. So you can buy a transformer and we will look at the nameplate. It will tell you this is a 50 MVA, 60 MVA, and 70 MVA transformer, right? So it's based on how the cooling system is functioning now, right? So this transformer can function at the 3 ratings based on how the cooling system is operating. So if you are leaving it to natural cooling, what's going to happen? There's an oil is filling it. Oil, when it gets hot, it will rise. It will go into radiator fins. So these are radiator fins. These on the side here. These are large fins for the oil to cool down, right? So when the oil gets hot, it rises. When it rises, the path is designed inside by the mechanical engineers, right? So this is an electrical device, but it's designed by both electrical and mechanical people, right? So the path of the fluid or the oil is such that when it gets hot, it rises, and then it forces itself through these radiator fins, and then of course there's a tank on top here to allow for any changes in temperature that make the fluid expand or contract, right? So if a fluid is heated up, it will expand as well. So you need to have a sort of a volume compensator if you want, right? So there will be a big tank for that, right? And then if you do this by a pump, then you're cooling the transformer better, right? So one way to do it is just keep it without running the pumps. And then in that case, the oil will, the heat from the windings will heat the oil, it will rise, move through the radiator, cool down, come back to the system, and you have a closed loop, right? And if you force this closed loop, then you're doing a better job of cooling, obviously, right? You're going to be forcing the oil to move around quicker, and you'll be able to cool the transformer better. And then if you do that and you add a fan around the radiators, for example, so these radiators maybe on the side, like your car radiator, if you open up your hood, you'll find your car radiator has a fan right next to it, right? So at some point, initially when you start, maybe the fan is not running. After a few minutes, then you'll find the fan running, right? So and this is an additional way of forcing the radiator to cool, the oil to cool down, right? So that's why it will have 3 ratings, because of the cooling system, right? So initially we just left it to natural convection. And then we forced oil to move. And then we added air so that we can remove the heat quicker from the radiator. So these will be the 3 corresponding to the 3 ratings, approximately. And we will look at what I mean by the 3 ratings on the nameplate of the transformer, right? So that's basically everything we have in here. This transformer also has gas-insulated switchgear, so it's pretty well enclosed, and you will find all the sensing devices inside it as well. So this is a pretty high voltage transformer, I don't know, maybe 400 or 500 megavolt ampere type transformer. And we will see how much oil, I have a nameplate of one of the transformers, and we'll show you what the volume of oil is in one of these devices here. So that's the picture dissected, yeah. So you see radiators here on this side, radiators on the other side. It's a huge device, yeah. Okay, so after we've dissected the picture. Okay, so as I said, the workhorse of the power industry is really the transformer. And it enables us to step up and step down voltages and currents like we know. Of course, it's constructed of 2 electrically isolating coils, and we will wound in the same core, and we will see why they're wound in the same core. We talked about that briefly before, and basically the core acts to constrain the flux so that it can link the primary and the secondary and produce voltage, and we will see how that happens here. And we talked last time about what would the transformer configuration be right after the generator. We talked about that last time. Remember, we said when you have a generator, what do you want to do to the voltage before transmitting it? You want to step it up, right? So, and we gave the different star delta, delta star, star star, delta delta configurations, and we said that the delta star configuration is great because it provides us some stepping up ratio for free. So we said that typically anytime after a generator you will find a delta star transformer. We went through that last time, so please review it if you don't feel comfortable, or ask me questions. And then anytime you want to start stepping down, we would typically use a star delta transformer because it provides a stepping down functionality for free, from a star to a delta on the secondary side. Of course, we will give some terminology here. So the primary winding is what is typically connected to the source, and the secondary winding is typically what is delivering power to the load. The induced EMF, we will talk more about that. It's basically proportional to the number of turns that we have in each of the coils. So it's not just a turns ratio, right? So if you want to operate at a certain voltage, there will be a certain number of turns you also have to satisfy, not just a turns ratio. Ideally, for an ideal transformer, maybe like you've solved before, you have 4 volts in the primary, you want 8 volts in the secondary, you put twice the number of turns in the secondary, and that's it, right? But to operate at 4 volts and to operate at 8 volts, you need a certain number of turns as well. That's why in 438, when you were playing and building the transformer in the 438 class, you use so many turns. Because at a certain frequency and operating at a certain voltage, you have to satisfy a turns ratio as well as a certain number of turns, right? And we will see that shortly. Obviously, if we need to step down, we will have less number of turns. If you want to step up, the winding that's stepping up will have higher number of turns. So a transformer with more secondary turns than primary produces a secondary voltage higher than the primary voltage. It's called a step-up transformer, right? So if you want to step up, you have more turns in the secondary than the primary, and vice versa if you want to step down. So, as I said, these large oil-filled transformers, you can typically find them up to 700 MVA, not because the electrical engineers are not good enough and they cannot design them, but it's because we cannot transport them. Right? They're very difficult to transport. They're huge devices. You cannot really transport anything larger than that. Yeah. The transformers are made of laminated sheets. So, can anybody tell me why? Yeah. So, what is eddy current? Sure, it's eddy current.
It's the current that flows in the core instead of the coil.
No. What do you mean? What do you mean the current that flows in the core instead of the coil? So you have a transformer like this, right? You have flux moving which direction? So if you have a winding, let's say you wind it in this direction, you have. Right, so current is moving in this direction. For example, you have your source supplying voltage here. Current is moving in this direction. So current is moving in this direction into this is what? Right hand rule. This is what? This is into the sheet. Into the sheet is the X, right?
Mm-hmm.
I have these X's here and the dots on the other side, obviously. So from the right-hand rule, the flux will be going to the top, directed to the top. So the cross-sectional area that is seeing the flux cross is this cross-section area of the transformer's leg here, right? So if this cross-sectional area is just one big conducting material, right? This is a conducting material that is seeing a time-varying flux. This phi here, this flux phi here will be a time-varying flux, because if you don't have a time-varying flux, we said that we cannot generate a voltage at all, right? So we will look at the equation shortly. But if we have this, if phi is a time-varying flux that is crossing, a big, nice cross-sectional area that is not laminated, then what's going to happen? This big cross-section area is nothing. It's like a short circuit, right? It's a big conducting area for the current to flow. So you have time-varying flux, and you have put a conductor in a time-varying flux. Put a conductor in a time-varying flux. What will happen? Current will flow, and then force will result based on that, right? And this force is basically what you hear. The transformer, when you drive by, has this hissing noise, and it's because the laminations are, pushing against each other actually. So it's the magnetic material is your the flux is changing its polarity, and the force is changing its polarity, and the laminations keep hissing because of the magnetostriction force that is resulting based on this. Okay, so what you do is, of course, you don't want, and of course, if you have a big cross-sectional area for the current to flow, then you have big loops of current flowing in this area, and the result is, if this is an electrically conducting material, that will also have losses, right? So these will be eddy currents that will create some losses in in the system, in the transformer. So you want to make sure that as the flux crosses, it sees smaller areas, right? So it creates less losses. You cannot eliminate eddy current losses, right? But you can decrease them as much as possible. So you would have to laminate or chop up each of these laminations. So these would be laminated so that you don't allow large eddy current loops to flow, and hence larger losses, higher losses in the system. So they are laminated to minimize the eddy current losses, as we said. And then these transformers, the oil type ones, so we said there are two types, dry type and oil filled. Oil filled ones are filled with oil because of insulation and cooling, right? So, and the dry ones, or the dry type ones, use air as the insulator, right? And then they use air as the cooling medium as well, right? They have air in there. Air is around the coils in there, and it's used as the cooling medium and the insulation. Of course, which is better as a cooling medium and insulation? Oil is better as a cooling medium and insulation. But air is still available. In air, the breakdown voltage of air is 30 kilovolt per centimeter. The breakdown voltage of oil is much higher. I don't know the number, honestly. Maybe 100 kilovolt per centimeter. So the breakdown voltage is definitely higher in one of these oil-filled transformers. And as we said, we want to insulate from what? We want to insulate from having any of the windings touch each other or touch the casing. So we have either air or oil as the medium, right? So if any of these windings touch the casing or touch each other, they cause short circuits, or they place voltage on the chassis of the transformer. And cooling, we talked about that, and we talked about the cooling fins and the convection cooling, natural and forced, right? So of course, under severe conditions, they can add water cooling as well. So you can have the oil cooling, you can have the fans as well. You can be pushing some water as well. So yes.
So the oil doesn't heat up.
So we were talking about that at the beginning. So if you see here in this picture, this is a different picture from what we were talking about. But here the fans are clear actually. So there are radiator fins. So the oil will heat up. Yes. So it will start rising. The fluid flow path inside the transformer is designed such that the oil will then flow through radiator fins, like your car. And then here we have the fans that are connected to the radiator. So behind the fans there will be radiator fins, that these fans are taking all the heat out of. And then of course you will have a balance of a volume sort of compensation tank here for the oil, so that when the volume increases or decreases, any overflow will go through the tank as well. So this is another transformer picture. Okay. Transformer oil is a very special oil, so it's a very super refined oil with very low moisture content. Moisture will actually ruin it. So if you have moisture, then if you have impurities in the oil at all, if you have any impurities in the oil, then what did you do for that? In the area that you have impurities, the objective was to insulate, right? You put oil in there to insulate. If you have any impurities in there, then what happens is the breakdown voltage in these areas is less than the breakdown voltage of the oil. So then what happens if these areas happen to be close to windings that have degraded the windings would typically have insulation wrapping around them. Each winding will be wrapped with insulation. This is typically it's cellulose paper. I think I wrote it here. It's it's a cellulose paper. Yeah. So it's a cellulose paper typically around the winding, and this paper can degrade if flashovers occur. So if you have, let's say, moisture will attack paper or attack insulation materials. If you have windings for water, for example, that's connected to polyimide. Polyimide is a very good insulator. It's an excellent, or Kapton. Kapton or polyimide is a very good insulator. But you bring water to it, it ruins it, right? So electrically it's great, but you cannot bring water. If it touches water, it will ruin it completely. So we put this. So we use, for example, the cellulose paper or Kapton or whatever you want to use, and then you fill this thing with oil. But then if you have moisture coming in, then for some reason it will attack this paper, and with time this paper will degrade, and then you have to keep sampling the oil. So that's one of the things that you would do. I mean, it's typically done at any industrial facility or utility. They would go and sample the oil. So they would sample the oil. I think I wrote that somewhere. Typically, the utilities typically sample oil from major transformers approximately almost every 3 months to make sure it doesn't degrade. So you take the sample of the oil and you go and analyze it, and you make sure that there is no moisture content increasing, there is no paper, the insulation material is not decomposing and flowing in the transformer. It's something that we condition monitor. It's called condition monitoring, or it's something. It's part of the preventive maintenance sort of jobs of any utility or industrial facility. So these transformers, they can last forever if you maintain them well, or if the windings don't degrade. But of course, everything has a lifetime, right? If you go and if you look at a piece of wire, the data sheet for a piece of wire, they will tell you that this piece of wire can operate with the insulation around it for, I don't know, 30,000 hours, 40,000 hours at this temperature and this voltage and this current, right? After that, what happens is it's degrading. It doesn't disintegrate, but it starts degrading, right? This is the lifetime of everything, right? Everything has its own lifetime. So similarly, the insulation has a certain lifetime, which is what's going to limit the transformer lifetime, right? So the metal itself doesn't go away, the copper doesn't go away, but what degrades is the insulation material, and of course it ruins the oil. So you would have to change oil, you would have to flush it out, you would have to, I don't know, if you want to, you can reuse transformers. So actually you can, they would throw these transformers away, and I've bought, for example, old transformers to take the laminations, to cut them up, and make a small machine, a new motor or a new transformer for research purposes, right? This stuff is available to buy actually after that. So it's not something you throw away. Or you can rebuild it, of course. You can take the windings out, rebuild the windings, oil fill it again, etc., etc. Is it worth it or not? I don't know the financials, honestly. So this is not very clear. I have a better nameplate. So this is a typical nameplate. I have a better nameplate with that. That is more clear, actually. Is it more clear? So let's see. So this is the 3 rating stuff that I was talking about. For example, this is called the load tap changing transformer. I'll talk about what this means. And it has 3 ratings. It's 24 MVA, 32 MVA, and 40 MVA, right? Not at the same time. It just means that depending on the cooling system that you're operating with, it will have either this or that rating, right? So either if it's, and here there's the list of the different types of cooling systems. There's oil natural, air natural, meaning no pumps or fans involved. And then oil forced, air natural. So the oil pump, you're running the oil pump. And then ODAF is the oil forced, air forced. So you're running the oil pumps and the air blowers. So that's one of where that comes from. On-load tap changer, or load tap changing transformer, or is what we see here. So if you look at this is the connection of the windings in the transformer. It's a bit funky and complex, but basically you have 3 phases coming in and 3 phases coming out and a neutral. That's really what you have in here. But you have a lot of taps on the primary, and you have a lot of taps on the secondary. These would be typically some measurement taps that you have here, but these would be all these taps on the physical winding itself is used to change the voltage. So remember, when we talked about the load profiles in a power system, we said that the load profile in a power system is not constant all the time, right? It keeps changing. You're consuming more power. This area is consuming more power. Ras Laffan, when they're during the day, they're consuming more power. Then they reduce. Then this area is consuming more power. Then this area is consuming more power. So the power consumption around the system is a time-varying function, right? And anytime you are consuming power, your current is flowing from the generators through the transmission lines to the loads. You have voltage drops around the system, right? If one area is consuming more power at a certain time, maybe the voltage drop on the way to that area is higher than other areas. So the voltage profiles in the system, there's a voltage profile in the system. It changes all the time. So that's why when we start looking at a larger power system or the solution of a power system circuit, like we introduced this power system as at the beginning, one of the most important things to us will be, okay, you'll be sitting at the utility and you'll be looking at the large power system, and we will have graphical, and PowerWorld is has a nice graphical interface. And this, using the graphical interface, you can show actually, okay, the voltage profile in this area is, 50% or 20% less than it's supposed to be, or 5% less than it's supposed to be. And you will have colors and numbers, and we will normalize numbers on the voltages and currents around the system for us to be able to sit back look at a big power system and say, okay, there's a problem in this region, right? If you have a big power system map in front of you and you see the voltage there being 15 kilovolts, you have no clue if this 15 kilovolts is good or bad, right? But if we find a way, and we will do that in this chapter, to normalize quantities around the power system, such that the normal is 1, right? Then I can put a huge power system in front of me as an engineer, and then I can, for example, I will put a color indication on PowerWorld that says, if the voltage in this region is less than 0.95, for example, change the color in this zone to something else, right? So we will have to do stuff like that. So, and the voltage, as I said, because of the voltage is changing all the time, the utility needs to make sure that it knows that this is happening and is controlling the voltage around the system. Because for example, if an area is consuming a lot of power and the voltage is dropping in that area, you want to make sure that you raise the voltage, for example, that's going to that area. One way to raise the voltage is to do what? Is to add reactive power, because if that area is consuming a lot of reactive power, there will be a voltage drop due to the consumption of reactive power, because generators are transmitting power through these inductive lines that are consuming the reactive power. So you want to make sure you compensate it. So one way to play with the voltage or change the voltage around the system will be through adding capacitors. Right? That's one way. The other way is what? Is transformer tap changing. Right? So, if the transformer, simply a transformer tap changer, basically does this. You have a transformer here, primary and secondary. Instead of feeding the secondary, for example, from these two windings, you feed it from, this is called a tap. So you're actually physically connecting to this winding. These windings will be physically available for you to connect to. Here, the voltage that you get here is less than the voltage that you have here, right? And you can do the same thing with the primary side as well. So you can be this can be moving up and down, for example, or you can have many of those fixed, right? Many of those that are fixed, like we have in this transformer. You have many of these connections that are fixed, or you can have something that it's motorized and moves, right? So you can have it can be on load tap changer or under load tap changer, meaning it can happen in real time while the load is connected. Or sometimes you have these taps available, but you have to disconnect the load, change the tap, and then re-energize the system again. Of course, the more expensive one is the one that can do this in real time, right? That can have a motor, for example, here, and this motor is automatically changing the voltage, right? It's a nice feature, but of course it comes at a cost. Why does it come at a cost? Because remember, this is an inductive load that I'm feeding, right? I'm feeding a huge inductive load, right? All my loads, I said, will be reactive, right? Will have a lagging power factor to a large extent, which means I have their inductive. Inductors don't like current to change abruptly, right? So if I'm feeding current here to an inductive load, and I'm gonna disconnect and then connect at a different voltage, what's gonna happen?
So current will change.
I will have arcing, right? Anytime you disconnect inductive current, we have VL is equal to L di by dt. Disconnecting inductive current means I change di from a large value to a small value. So di is large in a very short period of time. I'm changing current instantaneously in a very short period of large current, change it instantaneously. What's going to happen? I will have a huge voltage develop across my inductor. If I think of my system as this switch and my load inductor here and my source, then if my source is small voltage, for example, then basically this large voltage will be developed across the switch, and I will have arcing happening. If you have arcing happening, then this is submersed in oil, right? This is all submersed in oil. Then what's going to happen? You'll be burning that oil, right? If you burn that oil, then you're adding impurities to the transformer, right? You add impurities to the transformer, then your insulation integrity is no longer there, right? You lose the insulation integrity here. So this is one of the problems. So the way we would do it actually physically is we would make before break. So let's say I want to change from here to here. So I would live with, or let's say I want to change from here, from position 1 to position 2. I would maybe put a short circuit first around these two positions, right? I won't disconnect. I put a short circuit. I would live with a lower voltage or a higher voltage to my load for a while. And then, so I make first, and then I connect here, and then I remove this, right? That way I made before I broke. It's called make before break, right? So I put a short circuit across the two taps. So I short circuited the windings for a short while, right? Which is not good for the windings. It will heat them up, but they're rated for that, right? The on-load tap changer or under-load tap changer would definitely be more expensive than an off-load tap changer transformer, right? So they were more expensive. Why? Because the insulation has to withstand, for example, these short circuits for a while until you make before you break, right? And then the oil may be more expensive because of the fact that it's prone to these impurities being present. Of course, there's an automation system that goes along with moving this along, so it's a more expensive transformer. Can you live with it or not? In a residential neighborhood, maybe you don't care. If this is a major transformer feeding, a huge chunk of the city, you don't have a choice. You will buy one of these more expensive transformers, right? So that's all. I mean, I'm not going to go. So if you look at the nameplate, you will see. Let's zoom in here. You will see all the possible voltages in the primary and the secondary, and then they will tell you which tap configuration. Right. So these are. It's all. I think that the transformer is what? What's the voltage rating? It's 115 kilovolts on the primary, and then the secondary is 14.4 kilovolts in star, or 8.3 kilovolts in delta, right? So this is the high voltage rated. This is the rated value, right? So rated value, you can achieve it at a certain tap position, right? So these are all the voltages that you can get in the primary. All the different voltages. Of course, the rating will be somewhere in the middle. The rated voltage is 15 kilovolts. It's somewhere within the voltage that you can get. But depending on the tap position. So let's see. So where did they give the tap position? I cannot see it very clearly. Position 15R. So yeah, these are the tap positions. R connects, blah, blah, blah. So this is sort of the tap changer. H connects, so this whole box here sort of describes the tap changer. We definitely have to look at the manual of the transformer and look at, 12R and H. And so I think you'll find the different letters here, R's and H's, and the different numbers and M's. So you will find you'll find different numbers here, and you will have to go and look at the data sheet for the transformer to understand how, what these things are, right? So these are positions. These are all of these are different ways that you can connect the transformer, and the result is basically you have varying voltage at the input and varying voltage at the output, right? So if you play with the taps in the primary, you can change the voltage. Play with taps in secondary, you can change the voltage. How we do that for this specific transformer, I don't care. But the idea is what I showed you in the simple drawing for the single-phase transformer, right? That's the idea of the on-load tap changing transformer. And that's why we have all these winding taps or winding taps available for us to play with. Okay. The other important consideration, which we will spend a good time on, is the way we connect the windings. So this is a delta star connected transformer, and we will spend a lot of time on transformer connections, because what this will be doing to us is allowing us to play with the phase voltages between the primary and secondary. So remember, if we have a star-star transformer, and we look at the phase A voltage on the primary and phase A voltage on the secondary, they will be what? In phase, right? But if I have a delta star transformer, and I look at the phase A voltage on my primary of the delta, and phase A voltage on the primary of the star, are they going to be in phase? The phases, yes, they will. The phase voltages will be in phase, because it's a transformer, right? I put a phase, if I put a phase here, this is my, again, we will spend a lot of time on this, but I'll quickly look at it. Let me erase this 1 second and redraw it, because we will agree on something. So this is a transformer, delta star transformer. 1, 2, 3 phases. 1, 2, 3 phases. We will agree together, I think in the next class or the following one, that the ones, when we draw one of these transformers, that any of the windings that we draw in parallel with each other will be the same phase. So we will agree to that internally here, and this is sort of what electrical engineers like to agree to. So this one, for example, is we drew it here in parallel to this, right? Physically, the way we drew it here on paper, we drew this in parallel to this, right? So if I call this phase A, then this is V. This is AB, for example. This is phase A of the AB of the delta, or phase A of the delta. So this and this, the parallel windings, are on the same core. Remember, a transformer, the way we will come up, we'll draw the equivalent circuit now, but it's basically, we said it's two windings that are wound on the same magnetic core, correct? Right. This is the basic single-phase transformer. I can take 3 of these, and then I can connect them as delta or a star, whatever I want, right? But this winding and this winding are on the same core. They're seeing the same flux through them. So what is the voltage that's generated across the terminals of these windings? Exactly, it's equal to N d phi by dt. So, and they're in phase, right? So if the two windings are on the same core, they will be in phase. Okay? That's why when I said, if this winding here, I drew it in parallel with this winding. Okay, so let's agree that if I draw them in parallel to each other, that they will be on the same core. It's like they are on the same core physically. If they're on the same core, then they will have voltages that are in phase. Right? Do we agree with? Can we agree to that? Yes. Yes.
So you mentioned something about it having a root-free difference of magnitude and 30 degrees of.
Forget about magnitude. I mean, this is the line voltage. Okay, so let's continue. We will go through that in a lot of detail. But let's continue for a little bit here. This will be in phase with this. The magnitude will be depending on the number of turns here. But assuming they're 1-to-1, I will answer your question, right? And then this one. So this one and this one, we will assume in phase. This one and this one, right? We drew them in sort of parallel, so these will be in phase. And this one and this one, we drew them sort of parallel, so they will be on the same core, on the same core, on the same core, right? Now I can take my 3 windings on the secondary and connect them in star. or I take 3 windings in secondary and connect them in delta, right? What we were talking about is if my delta here was connected to a star, this voltage here is now equal to the line voltage of the star, is equal to these two. Right? I was talking about a different thing as we were talking about, and we will come back to your discussion maybe 2 classes from now. So let's not skip. For now, let's. For now, why was I talking about this? Because I was talking about the connections, right? So I was talking. So these connections will be very important to us. We will be drawing. You'll be drawing a lot of these things. Okay, you will be drawing the different configurations, and then I will ask you what is the phase shift between the line voltage on the primary and the phase voltage on the secondary, for example, line voltage on phase AB and then the phase voltage of this phase, for example. And we will figure out how to do that in a lot of detail, because it's very important. Because if you're doing some protection, if you're doing a protection engineering, if you're designing the protection of a power system, again, you cannot have phase differences between, for example, let's say you have to feed a load with 2 different transformers. This is how you resemble the transformers. You feed a load with 2 different transformers. And let's say this is a delta star, this is also a delta star, right? But you have, these are three, or 3 separate windings, and you're connecting them yourself physically, right? So you have to make sure that if you cannot just connect them anyway, right? You cannot just take one terminal here, okay, I'll connect these 3 terminals together. And then the other 3, I'll just put them anywhere I want. You cannot do that, because each of these phases here is related to the voltage that is across it because of the core that it was wound on. It was wound on, the ones with, again, that's why whenever we draw the ones in parallel, we would realize that, okay, if the secondary is in parallel with this winding here, then they will have the same phase voltage. So we will have to make sure, we will look at the phase voltage that is generated across each of the phases, and understand, if I want to create a certain phase shift on the secondary with respect to the primary, I have to figure out how to connect the windings exactly. You cannot just take any wire and put it anywhere, right? So, because if you do that, you may end up with a star here and a star here. But maybe the star here is shifted with the voltage here, across the line to line versus the voltage here across the line to line. This is 0 degrees and then this is 30 degrees. Can you do that? You cannot. I mean, instantaneously there are 2 different voltages. You will have currents flowing through them, between them, right? So it's not how you would do it. So we will spend some time on that in this chapter, quite a bit of time. And this is called vector groups. And the electrical engineering term, the power engineering term for that is called vector groups. So we will study these vector groups, and basically it's nothing but understanding how to connect the phases of the transformer, right? So that's something you will definitely find on the transformer nameplate, because if it's not on there, you don't know how to connect what, where, right? So the vector group of the transformer is an important consideration. The tap changing is an important consideration. The type of cooling is an important consideration. Here they give you the basic insulation level, okay? BIL is called basic insulation level. It's 450 kilovolts, right? So this is a 115 kilovolt transformer. The insulation is designed to withstand 450 kilovolts on the primary, and then 110 kilovolts on the secondary, right? So the secondary is a 14 kV. Your insulation withstands 110 kilovolts. Okay, continuous temperature rise. So I guess for the different ratings, so it's depending on what rating you're operating at, you will have the temperature rise will be about 55 to 65 degrees Celsius. This is a 60 hertz transformer. What else do we know here? Here, this is going to be very important for us. Impedance is 8.17%, right? You will be given this as a percent, and that's why we will normalize. They're giving you impedance as a percent. What does this mean? It means that forward-looking, this idea of normalization we will have to use, right? Because we are going to represent everything as a normalized number. Impedances will be normalized, voltage will be normalized, currents will be normalized to 1, or percentage. It doesn't matter. 1 or a percentage does not really matter. But we will have to normalize everything. So they will give you impedance typically as a percentage, or we call it per unit as well. What else is important? If you look down here, it tells you how much oil is in this transformer. So you have the core weight, the metal, just the core weight, the material itself, the metal magnetic material is about 64,000 pounds. The tank fittings and radiators about 38,000 pounds, and the oil main tank is 4,000 gallons. Oil tap changer compartment is 100 gallons. Oil radiators is 690. So you have a total oil of about 5,000 gallons of oil, and this is a low power transformer, right? It's how much? We said it's a maximum 40 MVA transformer, right? And you have 5,000 gallons of oil. So can you imagine how much you have in a 700 MVA transformer? A huge amount of oil, right? So it's a big bulky device. Yeah. It's a huge bulky device. Yeah. So this is a typical nameplate and all the important, interesting materials on it. I think the Bushing current transformer. Yeah, so they have these things here are actually as measurements, right? And these they will have actual CTs, the actual current transformers installed in the transformer already. So here they tell you the ratio is here of the CTs. So bushing current transformer. So the insulator that's coming in or the insulator that's coming out is called a bushing. Okay, and they've installed these current transformers on the bushings themselves, and the transformers they've installed. So this is the X2 to X3. X2 to X3, if you measure between X2 and X3, if you measure the current between there, then the ratio is 50 to 5. So if you have 50 amps in the coming in into this phase or out of this phase, then you'll be measuring 5 amps on the X2 X3 loop, right? So they have that for you here. Why do we have these current transformers installed in there? Because we will need to protect the device. When we talk about protection, we will see how we protect the transformer itself, how we protect a larger power system, or a smaller part of the network, a larger power system. We'll talk more about that. But you will have some of these installed already. So that's what all these things on the incomings and outgoings are. And why do you need it on the ground one as well? Why do you need to measure current on the ground connection or the neutral connection as well? Yeah, because we want to make sure that there's no unbalance. If there's an unbalance in the system, or for some reason, if there is a short circuit between any of the windings and the ground, like if any of the winding insulation is bare and it's touching the transformer, then we want to make sure that we measure that and we protect against it right away, right? So we have these current transformers and voltage transformers. Here, these are voltage transformers probably, yeah. So you'd have the protection devices sometimes installed on the device itself. So any questions on transformer generally? Driving mechanisms. So this is an on-load tap changer. It will have a motor to drive the tap changer. Number of turns of the crank for each operation. So anyway, so this is just some general stuff I wanted to share with you. I think it's important to know some of this general stuff. Okay. The boring stuff? Okay. What? Any questions? And now you're going to wake up? I'm just kidding. Okay, so let's see what we're talking about. So simply, again, we discussed this idea of, the transformer being basically turns wound around the core, right? And we know that, again, if we have a certain number of turns wound in a coil fashion, and we have flux linking that. Flux linking it meaning flux going around it, right? So there's flux linking number of these turns, meaning flux is going around these turns, or through this time varying flux is going through this turn of coils, yeah. If time varying flux is going through these number of turns, then the voltage that is developed across number of turns is equal to N d phi by dt, so it's proportional to the number of turns. So if we make this flux sinusoidal, then the voltage will also be sinusoidal. right? Since they're related by differentiation. If this is a sine, this would be a cosine, cosine would be a sine, right? So it cannot be DC. That's why if it is DC, what happens? There is no E developed. If there's no E developed and you put a voltage source across the winding, what happens? What do you mean nothing? No, something big happens.
An arc.
You just woke up? Okay. Huh? No, not an arc. Come on. You have a set of turns and you put a voltage source here. Okay, wait. Let's go back to the case where there is time varying flux linking these coils. Okay, if there is time varying flux linking these coils, then what will happen is across the terminals here, I will develop a voltage E, right? If I have a voltage E here, and now I put a voltage V here, what will happen? If V is a little bit greater than E, what will happen? If V equals E, what happens?
Steady state.
Zero current will flow. No, zero current will flow. Yeah, zero current will flow. If V is a little bit greater than E, then current will start flowing, right? So if current starts flowing, and is it going to be a huge amount of current?
Yes.
Why?
In the beginning.
Initially it was zero. If I just said it's a little bit greater. No, it's not the idea of resisting the change, but it will be a small current because V and E, the difference between them is very small in this case, right? But if this time varying flux goes away, then, and I keep the same voltage that I had before, what's going to happen to the current? It will be a huge current because there's no E. E is okay, when you do a Kirchhoff voltage law, right? E was doing what? E was opposing this voltage. E was opposing this voltage. So if E exists, then the current flowing here depends on the voltage difference between these two. If there's no voltage difference, current will not flow. If the voltage difference is very slight, small current will flow, right? Only a small amount of current will flow in this case. But if E does not develop, I have a voltage source across a piece of wire. There's no E developed. E will not develop. This is E is zero. Then I'm putting a short circuit across my source. That's why transformers do not like DC. If you try to put a DC load across a transformer, DC source across a transformer, what will happen is that you will saturate the core, and that's it. You will increase flux in one polarity, and that's it. You will not have the time varying flux. If you don't have the time varying flux, you don't have a back EMF voltage developed. You don't have a back EMF voltage developed. You basically have a short circuit across the transformer. Okay. Okay. So now let's say we put a sinusoidal flux, and we know that the voltage is basically the differentiation of the sinusoidal flux. So let's say we take this and we differentiate that. We get what? Yeah, omega cosine, omega phi max, right? Multiplied by an n as well, if I'm looking at voltage. Then I will get n, and the differentiation of the flux. The differentiation of the flux will be a cosine wave multiplied by n multiplied by omega, right? And is it going to be leading or lagging? If this is a sine, the differentiation is a cosine. Cosine will be leading by 90 degrees, right? So I have a waveform that is leading by 90 degrees, multiplied by number of turns, multiplied by omega, multiplied by phi max, which is what I have here, right? If I take the maximum and multiply by cosine, blah, 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 right? And then if I take the max value of that, the max value of that is this Emax voltage. This Emax, the maximum value of the voltage, is 90 degrees. So that's why this J is here. It's 90 degrees from the flux. And you multiply by omega, multiplied by n, multiplied by this phi max that you have. Sorry, I forgot the subscript here. Okay, so that's the maximum value of voltage that we have. If you want to write this in RMS form. So if you take, if E is divided, if it's divided by square root of 2, so you divide this 2 pi by square root of 2. So 2 times 3.141 divided by square root of 2, you will get 4.44, right? So 2 multiplied by 3.16 something, and then divided by, here, I think I did it before coming. 2 times 3.141, right? Divided by square root of 2 is 4.44 that we have, right? That's where this 4.44 comes in, right? So now this is an important equation. What does this equation tell us? Yeah.
What happened to the J? Is it still supposed to be there? Or?
What happened to the J? This is max value. I dropped the RMS magnitude.
Oh, okay.
This is showing you the phase shift between them. Just the RMS magnitude, sorry, the RMS or effective value only. Just the effective value, the magnitude of the RMS value of the voltage, right? So what is the relation? What does this relationship tell us? For the same voltage, right? For the same voltage, if I would like to design a transformer, I will have a certain number for the same voltage at a specific frequency. I will have a certain number of turns, right? And then if I increase the frequency and maintain my voltage, what does that do? So if I increase the frequency and maintain my voltage, I can live with a smaller number of turns, right? Or if I would like to operate at a higher voltage, instead of increasing my frequency, instead of increasing my number of turns, what I can do is increase my frequency, right? If I'm able to increase my frequency and not increase the turns and still go for a higher voltage, what does that mean? Turns means what? Turns means space, right? So it means that if I'm able to increase the frequency and operate at a higher voltage without increasing space, that means a transformer that is a higher frequency will be smaller. That's operating at the same voltage, right? So that's something that we play with. And that's why there's a lot of people now, if you look at what's happening in research, right? People talking about the future DC substations, blah, 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 or the future electronic transformers and stuff like that, okay? Or the future solid state substation. Yeah, that's the terminology that you can Google search, okay? The solid, that's a smart grid and, solid state transformer. So what they're doing in that case is what? You need a transformer to step up and step down. You cannot live without a transformer. To step up and step down, this is the best way to do it, yeah. So what people are doing now is, adding power electronics. You bring in, you have 50 hertz coming in, you want 50 hertz coming out, right? But you don't want a huge transformer. You want to, again, we saw how big these transformers are, right? So you want to live with a smaller transformer. So what people do now, or they're trying to propose as the future solid state solution to power distribution, is you bring in your 50 or 60 hertz, you use power electronics to convert that to high frequency, put a high frequency transformer in there, and then use power electronics again to bring this AC high frequency to 50 hertz back again. That way you're doing what? You're able to increase this frequency from, instead of 50 hertz, you're able to increase it to 100 kilohertz, right? So can you imagine, if you're able to increase it to 100 kilohertz, the size or number of turns you would need is a lot less to operate at the same voltage, for example, right? So you can live with a much smaller transformer in that case. So people are proposing that as a way to upgrade substations. So now the city is growing in this direction. The city is growing in this direction, the load is becoming much bigger. What do? I need a huge transformer. Instead of putting a huge transformer, okay, put in one of these new solid state substations. It's almost the same footprint that you will have before, but I can get much higher throughput and power because I've added some power electronics to it, right? This is one of the hypes, and you also get additional advantages when you add power electronics, right? Let's say you have voltage fluctuations, right? Then you have power electronics at the input and the output. So any power electronics can do anything with voltages and currents, right? Voltage is dropping, okay, boost it. Voltage is increasing, so step it down. right? So with power electronics, you also get these additional benefits. So you can get improved power quality, and that's what people are also proposing. Okay, now to sell this idea, you cannot just sell it as a replacement to a transformer. You have to sell it as a replacement to a transformer plus other nice benefits, right? Wow, you can also connect solar energy to it. Of course, you have power electronics. Anytime you have power electronics, you can do whatever you want, right? So they, or you can also add storage. I add storage. If I lose power on one side, then you can still supply your loads because I have built-in storage. So you can add all of these things anytime. Now I've added power electronics into the system, right? So I've decreased size of transformer, but maybe for the same footprint, I've added maybe some more storage, and now I can get improved power quality, ride through for faults. I can get feed the load for the next 10 years without upgrading to a higher, bigger transformer, etc., etc. So all of this is interesting. Yeah. Okay, so we'd like to look more into details of the transformer's equivalent circuit before we start looking at single phase. Before we start looking at three phase. So we drew this before. We have a core with windings around it for the primary and windings around the core for the secondary. And because it's the same flux that is linking both sets of coils, we know that it's the same voltage. That these voltages will be E1 and E2 voltages will be in phase. Do we agree? E1 and E2 voltages will be in phase. Or the voltages, across the windings. Here I don't have a voltage drop across this yet, so terminal voltage is equal to the winding voltage, and this for the ideal transformer. Right. Next, we will add some more complications, and we look at the more detailed equivalent circuit. Yeah. Anyway, so what Ampere's law tells us is what? Is that the integral of the magnetic field intensity around the closed loop is equal to the current enclosed. Right? Where is my closed loop? This closed loop here. Right? And what is this I enclosed by this loop? So let's look at this cross-section of the transformer. If windings are coming in here, then I have on one side this, and on the other side, right? The way we drew it, we drew a transformer like this. And then on the outside, on the other side, it's like this. So current is coming in here and out of the secondary side, right? So if you do the right-hand rule on the primary side, flux will be directed up, right? Flux will be directed upwards, and current will be coming into the page on this side. How about here? Current is coming out. Current is coming where? Out. What? No, it should be the opposite now. Then I drew it wrong. Yes. Yes, and it should be going up, sorry, and they will be subtracted from each other.
Yeah.
They will be subtracted from each other, sorry, I agree. And let's look at the equation and see. They will be the result here. This will be the n times Im. Okay. Yes, you are right. It will still be going up, right? If it's the right-hand rule, flux will be going up. So the difference between these two will be the flux flowing in the core. Okay. Think of it. If there is a difference between them, it's because of what? It's because the reluctance in the core required some additional flux to build this magnetization system, right? Because again, the number of turns here multiplied by the current coming in, number of turns here multiplied by the current coming out. Ideally, for an ideal transformer, they should be what? If the transformer is lossless, they should be equal, right? If I have MMF or number of turns, if I have the same number of turns primary, same number of turns secondary, that means current coming in will equal current coming out, right? This is a lossless transformer. Do we agree? This would be a lossless transformer. If there's a difference between them, then it's because the core has certain reluctance to the flow of the flux, and it requires some additional current. Do we agree? And that's what we have here. So the difference between them will typically be 0 for an ideal transformer. If there's a difference between them, it will result in some magnetizing flux that is required for this core to operate and generate this transformer action. So, and this is N1, I1, N2, I2. So for now, we will say that the I enclosed is the difference between them. Do you agree? The difference between them is the I enclosed, because the difference between them is what's generating these opposing fluxes. The difference between these opposing fluxes is what is generating this flux in the magnetizing flux in the air gap, in the core. Okay? So let's first write it down and then see. For an ideal transformer, we will assume that this flux that's flowing in the air gap has no reluctance to it at all. The core is ideal. There's no losses around the core, so there's no additional effort required to push flux to the core. It's 0 reluctance, right? So for now, let's say, okay, the H.dl is equal to I enclosed, meaning L is the length of this path here, and H is the magnetic field intensity. And this, we will call the magnetomotive force. So this is equal to N times some current. This current here is equal to I enclosed. I enclosed is now the difference. What is enclosed by here? What I have enclosed here is by this loop. I have these currents and these currents, right? I have N1 times I1, and then minus N2 times I2, because they're opposite directions, right? They're opposite directions. That's why we said their fluxes will subtract as well. Do we agree that this is I enclosed? N1 times I1, this is my path here, my closed path. If I assume that the direction that we had up here, right, then I have these coming into the page and these coming out of the page, and all of these together are I enclosed, so that whatever's I enclosed is the difference between the currents, right? So that's what I have here, and I will call this difference between the currents, assuming that the same number of turns here, they assume that the same number of turns, I will call it IM, right? I will call it IM for now, and this I will call the magnetomotive force, right? The magnetomotive force is basically like a voltage in an electrical circuit, right? A voltage, if you have a voltage source and a resistance, this voltage source will overcome the resistance impedance and push current through. If there is no resistance, if the resistance is if there is no impedance to the current, if there is no impedance, I don't need any magnetomotive force to link the primary and the secondary. So it's so let's say there's current coming in and there's current coming out. Current I1 is coming in and current I2 is coming out, right? If this core had some impedance, right, then I1 would equal to what? I2 plus the current required to overcome the reluctance of the core, right? It's the current. It's I2 plus the current required to overcome the reluctance of the core. That's what I1 is equal to. If the reluctance of the core does not exist, so I will say phi. If the reluctance of the core is 0, then this IM will also be equal to 0. I don't need this magnetomotive force component will not need to exist. The magnetizing component will not need to exist. So here it's I think we wrote it here as well. So the magnetic field intensity in the core multiplied by the length is equal to N1I1 minus N2I2. For now, we will assume N are equal, then we will call this N1I1 minus N2I2, we will call this N times Im. If this N times Im has a value, it means that this core has impedance to the flow of the flux, and hence you will require some magnetomotive force to create transformer action. If this difference is 0, then we have an ideal transformer, and it's nothing but voltage and current coming in is equal to, power coming in is equal to power coming out, exactly. Okay? So here, the magnetomotive. So one way of conveying winding information is to place a dot. We'll look at the dot thing next time. We said the magnetomotive force is equal to the difference between the ampere turns in the primary and the ampere turns in the secondary, and that's equal to the core reluctance multiplied by the flux. And we will have some dot notation, so we will assume that on the primary, current comes into the dot, and on secondary, current comes out of the dot. With that assumption, we have this voltage polarity. If I put the dot on the other side, I will flip the voltage polarity. And we will look at examples of that, and we will want to use that when we want to play with this phase shift stuff that I told you about. Vector groups, we want to develop different vector groups, we will play with the dots, with where we place the dots on the cores. So we will spend some time on that. So let's look at the ideal transformer. The ideal transformer core has infinite permeability. If the core has the permeability and reluctance are reciprocals of each other, right? So if the core has infinite permeability, it means it has zero reluctance or small reluctance, right? Which means what? It needs an extremely small Im to set up the flux phi, right? So N1 minus N1I1 minus N2I2 is or if the n's are equal, it's n times Im, right? Assuming the n's are equal, that this I1 minus I2, right, we call it n times Im. If the core requires or has no impedance to the flow of the flux, then you can easily set up the flux, right? It's like a short circuit. Like if the resistance is 0, you need a very small current. Then the voltage that you need to put in there is negligible, right? If you have a short circuit, then you almost need a 0 voltage, 0 plus voltage to set up the flux or to set up the transformer action, right? That's what this means. So magnetizing current will not exist, or will be very, very small in this case for an ideal transformer. And there will be no power loss, so I assume no resistive drop, even though these windings have resistances, right? So I assume that these windings have 0 resistance. I also assumed what? I also assumed that if I wind a winding on top of the core, around the core, that all the flux that's generated by this winding is going to flow in the core, right? And that's not true. There will be some flux leaking. Again, it's like any electrical circuit, right? If you have any electrical circuit and you have current flowing into 2 resistors in parallel, right? Some current will flow here and some current will flow here all the time, right? The ratio of them will be different. If you have if the impedance to the current is high, then low current will flow. And same thing with the flux. If you have a core here and you put windings around the core, most of the flux, okay, this is flux that's generated by the core, by the winding and current flowing through it. This flux will either flow through the core, or the other parallel branch is what? Through the air, right? It's like a current flowing in 2 resistive circuits, right? This is air and this is the core. It sees air and it sees the core. Some will flow through the air, some will flow through the core. So does this exist in an ideal transformer? No. In an ideal transformer, we will say that this air component does not exist. Everything will flow through the core, right? So in that case, we will need to come up with an equivalent circuit. So we assume certain things and we'll come up with an equivalent circuit for a transformer. We assume no magnetizing branch current. We assumed no power loss. So the windings have no resistance. We assumed perfect coupling, meaning all the flux is flowing to the core only, right? So then we have, and the magnetizing current required is pretty much negligible, zero. In that case, the equivalent circuit for a transformer will be something like, will depend on these equations, which we will discuss next time. But basically, the voltage will be exactly in phase, and E1 and E2 will be in phase. How about V1 and V2? What? Yeah, since they're so they're in phase and exactly equal as well, right? So I can draw an equivalent circuit. I can draw a phasor diagram for this system right now, where I know V1, E1, and E2. I know all of them. And if E2 has, if there's number of turns here, different number of turns here, then this E2 and E1 are just different magnitudes, but they are in phase. How about V1 and E1? They're in phase, equal magnitude. How about the flux on the phasor diagram? Where is it going to be? The flux is leading by 90 degrees, or is the voltage is leading by 90 degrees? Right? Yeah, like E equals N d phi by dt. So if it's a sine, the flux is a sine. If the flux is a sine, the voltage is the cosine. So the voltage will be leading by 90 degrees. Right? So I can draw a phasor diagram quickly, right now, for all the voltages and currents. Right? So if I place a voltage V1 on the primary of the transformer, this V1, because I assume the lossless transformer, is equal to E1, which is the voltage generated across the winding. But this voltage has not been generated yet, right? I put V1, and because I've put V1, this V1 is seeing a winding that has certain impedance, that will cause current to flow. When current flows, right? When current flows in this winding, if this voltage is sinusoidal and the current is sinusoidal, then it will generate a flux around that wire that is sinusoidal in nature. This flux will be lagging by 90 degrees my terminal voltage, and this flux will also generate a back EMF E1, right, across the winding. Right? Remember, initially I had no back EMF. The transformer does not have a back EMF. You put voltage causes current to flow, this current causes flux to develop. This flux generates a back EMF voltage E1. Right? It also links a coil on the secondary side generating voltage E2. Right? That if now E1 and E2 are not equal because number of turns, then this is E2, for example. Let's say it's a step-down transformer. This is my transformer, right? And of course, this phi1 was generated by a component, because V1 created a current. This current was where? This current is basically storing energy in flux, which is represented by an inductor, right? Current in an inductor lags by 90 degrees. So the magnetizing current that generated this flux is 90 degrees from the voltage that caused it, right? Because I resemble flux producing components with flux around them as an inductance. So this voltage caused current to flow in an inductive type element and hence produce flux. This flux produced the back EMF voltage across winding 1 and the back EMF voltage across winding 2. Now I can connect a load across secondary winding. This will be at a certain power factor. I don't care. Right? So this will be the equivalent circuit of the transformer. So we'll stop here. Next time we'll go over it again and continue.